Today we'll talk about two asteroid missions, one just launched and one just returned. First topic is going to be Psyche, which is a mission to a metal-rich asteroid. Now, Psyche is the name of the asteroid, and it's also the name of the mission to it. The spacecraft you see in the picture here is the one that's going to it. Part of that picture is cut off, but it is symmetrical in the solar arrays there. It just launched on October 13th and on a Falcon Heavy, and it will arrive in 2029, so you have to wait a while to get results from this. It takes that long to get there. It'll orbit it for at least 26 months, but probably forever. There's probably not going to be enough fuel to actually go anywhere else after that, so it'll be there essentially forever. That's the plan anyway. The launch is on a Falcon Heavy, and this is just before ignition really cut in. If you look closely through the haze of all the fuel vapors, you can see there are indeed the two side boosters, which of course land again after the center core takes off. So why does anybody want to go to Psyche anyway? Two reasons, really, major ones. One is scientific and the other is economic. The scientific, that's what drives decisions right now, certainly. This is the first visit ever to a metal-rich asteroid. We visited, well, actually I should say the Japanese have visited two other asteroids in the past and returned samples from them. This is actually the largest of the metallic asteroid. There are only about 9 that are known that are heavily metallic like this, so this is kind of a big deal. It might be part of the nickel-iron core of a protoplanet, meaning one that was in the process of forming and never completed, or maybe one that got smashed up just due to collisions with other asteroids. We don't quite know. Hopefully we can learn more about that. You think about it, we don't even know that much about Earth's core. We have rough ideas, but that's why scientists are so interested to see, well, what's there? Because we can actually go look at that. It's cold. You don't have to go and get melted, to go see it. And of course, this will give us clues in general about the formation of the rocky planets. Now, the other reason for the long term is it's metal rich. Like I said, the Japanese have visited two other asteroids. Those are mostly carboniferous asteroids. They have a lot of carbon, loose piles of rubble. This one is truly different. The prospecting angle is unique because sooner or later, that is a lot of metal, and we're going to want to use that. And it probably isn't going to be economical, at least with the current technology and for quite a while, to ever really bring that back to Earth. But once the space economy gets going, there's enough metal here to power it for centuries. So, there's definite reasons to visit this. So some fun facts. It's about 173 miles at its biggest dimension. It's potato-shaped. Now, they had an interview with the lady who is the principal investigator for this project, and she admitted that, well, actually potatoes can be shaped like almost anything. So we say that asteroids are typically potato-shaped because we're never wrong. So surface area, roughly the size of Texas or California, take your pick. None of these things are known exactly. They're all estimates because it's still pretty far away and it's not that big. But they do have estimates for a variety of reasons. You can look at things like what are the perturbations of orbits of objects near it. You can look at the light reflected from it and try to derive information about what it's made of. So there's been a lot of study of this asteroid. And they have concluded that its density is between 212 and 256 pounds per cubic foot. So to put that in perspective, water is at 62.4 pounds per cubic foot. So that's one density. Rocks are typically heavier. Most of them, maybe by a factor of 2 or so, and this is more so than that. So that's one of the reasons they're pretty sure there's a lot of metal in here. The metal is heavier in general. The mass of this thing is 1% of the mass of the entire asteroid belt. Again, these are all estimates, but it is the best that we have so far. So that kind of says this one's worth going to. It is the biggest, and let's go there. So eventually it'll be mining, and of course people immediately say, well, gee, what would that be worth? Making some rough estimates on the metals that are there. They say, well, that's worth about $10 quintillion, and that's plus or minus a couple of orders of magnitude. Your estimates may vary. But of course, it's not realistic because we don't have any technology really to mine it right now and to get it back to Earth and get it down to Earth. So again, it's really more of a long-range play. Estimates vary at between 30 and 60% metal by volume on this whole thing. So the key thing here is that, yeah, maybe we're not going to be mining it right away, but it's a reminder that the resources in space are vast. They totally outclass just the tiny little bit that we have on Earth, and we just need to get there and get started. Once we ramp up, there's just a lot more we'll be able to do. The ultimate use is really manufacturing in space for use in space. Now, there have been changes over time in the estimates of how much metal there is. On the left-hand side of this diagram, there's an earlier artist rendition of what they thought this asteroid might look like. And you'll notice it has a lot more metallic gray-looking stuff. That's because they thought it was like 60%. Now they're thinking, well, maybe it's more rocky than that. So you can see the updated version. You know, the updated version's changed, but pretty soon we'll find out what it really looks like. Finally, you can see a picture of the entire spacecraft here. By the way, that part in the center is about 3 meters or so. It's about 10 feet at its biggest dimension. The whole thing with the solar arrays extended is about the size of a tennis court, almost as big as a tennis court. And what's the payload? Well, first of all, they want to analyze what this stuff is. So they have several ways of analyzing. One of the ways is visible spectrum. They can try to look at different wavelengths of light, and they know that different elements reflect things differently, and so they can guess that. They have these other spectrometers based on gamma rays and neutrons, and those are kind of interesting. That's because they assume there's background radiation, cosmic rays and so on. There's gamma rays, and there's also just neutrons that go flying around. Based on how they interact, they can actually make judgments of what's there. And that's something you can't actually do on Earth because too much stuff gets absorbed in the Van Allen radiation belts and air and so on. They're also going to study the magnetic fields. Of course, that's tied into the fact that it was an iron core. So things like, well, did it have a magnetic field? That probably would indicate that, well, it was probably rotating at one time. And there's all kinds of things they can derive from that. They can figure out better estimates of the mass and the rotation by looking at things like Doppler shift of radio waves. Things that they can do just even with position and radio analysis. And a totally independent test of this, for the first 2 years of this trip, which is before they get to the asteroid, they are going to experiment with laser communications. It could be much more efficient, potentially. The trick, of course, is can you keep it aimed? So during the first 2 years, except when there's occlusion by the sun or Earth, they will be attempting some laser communications. So that's kind of a separate, independent, but important test. In terms of the design, strangely enough, it's pretty much based on existing geosynchronous satellites, specifically the ones built by Maxar. They were the main contractor on this, which is kind of interesting because it says that they really thought that the radiation environment of a geosynchronous satellite is not that different or not that much worse or better than what they're going to experience out there. So that was kind of interesting because part of the rationale for NASA's Gateway project is that we'll get more experience with higher radiation environments. The reality is this other part of NASA figured out that it is about the same. You know, the geosynchronous satellites, they're in actually the upper area of the Van Allen belts. So if anything, maybe it might be a little bit worse. So anyway, they're expecting that. Now, there are differences, though. If you're designing a craft like this, there's big differences in the solar power because you're so much farther away from Earth. Of course, you have a lot less of it. And so they have to account for that. And thermal management. One of the bigger problems for satellites up in space around Earth is keeping them cool enough when the sun's shining on them, and then warm enough when they're eclipsed by the Earth. And here, they're so far away that the main problem is going to be keeping things warm enough. So there are some differences. But fundamentally, the satellite bus, the electronics, and a lot of that was pretty much derived from existing satellites. The mass of this thing, a little less than 6,000 pounds, of which 3,600 pounds is actual material, the rest of it's fuel. The payload, there was the part where we're actually trying to get there, that's only 66 pounds. So you kind of think about this. This 5,700 pounds, this is actually the payload for the Falcon that launches it, which is huge. I mean, many, many tons. And then this thing itself still is a rocket that has to get out there and deliver. And even at that, we're only putting 66 pounds there. That's why it's expensive. The large solar arrays then will account for the distance from Earth, as I said, about the size of a tennis court when you expand them. And to get a feel for the challenge this is, near the Earth, you'd get about 21 kilowatts of power out of these arrays. Out at Psyche, it'd be between 2.3 and 3.4 kilowatts, so it's quite a drop. And this is why traditionally most of the really deep space probes have typically had radioisotope generators, because they just put out the heat and electricity on a regular basis. They decided they could get by without any of that, just using solar. That does say they have to have batteries on board, because there are times when there's no sun, so they have to have that. As far as what this looked like, this is part of the solar arrays. Obviously, they have to fold up when they launch them, and then they expand them. In this case, they expand them 2 ways. Out 3, and then there's 2 more on the side, and then there's 2 of these. So they're pretty good size. I included this diagram mainly just so you can see the picture of the person to get a feel for, okay, it's bigger than a person, but it's not immense. This DSOC on the left-hand side here, that's the laser communications experiment. That's kind of just bolted on to the rest of this. Thrusters are down at the bottom, spectrometers and communication antennas for the Earth up there on top. The electric repulsion is kind of interesting. First of all, it's a xenon Hall effect thruster. And what is that? Well, that one is used on lots of satellites now. At least 30 of those geosynchronous satellites use a variation of this particular thruster. By the way, it's named for Hall. Now, Doug Hall, of course, is sitting right here. However, this is not you. This is Edwin Hall. He lived back in the 19th century. He's the one who discovered the Hall effect. What that is basically the interaction between flowing electrical current and magnets. So if you have a flat surface with current flowing through it and a magnet going in one direction, the electrons then move in the third perpendicular direction and set up a difference in voltage. That's the basic principle, but somehow or other they harness this in kind of a circular form and they make a motor out of it instead. Anyway, there's 4 of these things. These things take 5 kilowatts of power. Now, there are some that are bigger than that, but these are the ones that are in commercial use. They had to modify this so they could scale it down for use when they're way, way out there, down to like 0.9 kilowatts. Now, the thrust, though, is really tiny, 0.06 pounds. Essentially, think the weight of a AA battery. The weight of that you feel pushing against you, that's the force you're getting out of one of these motors. That's at 5 kilowatts. And of course, it's less than that when you have a lower current. But the reason people use these is they're extremely efficient. The efficiency measure usually used is specific impulse. That's 1,800 seconds, totally dwarfing anything we can get out of chemical or nuclear so far. For instance, the Merlin engines, they're the ones used on the Falcon 9. They're maybe 300, less than that for atmospheric, a little greater than that for vacuum use once you're out in space. These things are so efficient. You're spitting out ions, but it has to be ions from something, and that's xenon in this case. They still have to carry about a couple thousand pounds of that, but that's probably about 10% of what they would have needed with standard chemical engines, so it saved quite a bit. This picture on the left-hand side shows it in operation. You get this bluish glow, very nice, satisfying science fiction kind of look to it, right? Everybody loves that. The right-hand side is what it looks like when it's not in operation. Now, this one is a little bit different than a lot of launches in that there is absolutely no chemical propulsion once it's launched. And once the Falcon Heavy is done, that's it. Everything is just electric, and that's a little bit different. However, there are still what are called cold gas thrusters, which every rocket has. And they're like the simplest kind of engine you can have. You basically just have a tank full of a pressurized gas like nitrogen in their case, and you just open a valve and it goes shooting out, in compressed form, and that gives you thrust. You ultimately need some of that. For instance, if you're tumbling and you're out of control, you might not be getting enough solar power, or if you happen to be in an eclipse behind an asteroid or something, you might not have electrical power. So you need to have something that will work. And that is actually why every rocket has these cold gas thrusters in one form or another. Yeah. Oh, the company that makes it? I'm not sure. It all goes back to Soviet technology, actually. I'm not sure who actually finally built this particular one. You mentioned SpaceX. Every one of their Starlink satellites has Hall effect thrusters. They're probably a little smaller than this, but there's a couple differences. When they started out, they said, xenon, that is apparently really efficient, but krypton is a whole lot cheaper. It's actually 1/10 the cost. And so they started off using krypton. And they take a bit of a hit on efficiency, but it still isn't too bad. Now, actually, their version 2 satellites, their version 1.5 even, they're down to using argon. They switched, and they actually made them more powerful than the krypton version quite a bit. And that's another factor of 100 cheaper. So xenon, extremely expensive, of course, but it's traditional, and so that's what they're using. Other developments have made these things a lot cheaper to work with, SpaceX specifically. Actually, Blue Origin is using engines too, but they're still using krypton. Moving on. So the journey itself, this is kind of a busy diagram here, but you got the sun in the center of this thing. You got the blue circle representing the orbit of Earth. You got a red one indicating Mars. And then on the outer band here, you have Psyche. It's not the scale, but they're giving the idea here. So you launch. This is actually a quite simple orbit compared to almost every other one we've looked at lately. They pretty much just go and they get one gravity assist by flinging by Mars and getting pulled along for that. One gravity assist for Mars, and that's it. Now, the whole thing takes many years to get there, but it's a lot simpler than these ones we've looked at recently if you're going to the moon, where you go out and back and all over the place. Now, the end point, once they get there, then, of course, they're going to orbit around Psyche, and they start off, they say, well, they don't really know enough about the structure of Psyche. They think that it's very non-homogeneous, meaning there's some places where it's really, really metal and other places where it's mostly rock, and there's big craters. There's at least 2 big craters, I'm pretty sure of that. So all that says the gravity varies quite a bit. It doesn't have things like, you have on Earth that tend to even out all those variations. It's frozen in place, so that gravity is really very, very erratic. As a result, picking out a stable orbit isn't that easy. So what they're doing is they're just going to circle around it from a distance at first, and they're going to map it and they understand what the gravity looks like, and then gradually work their way down. Then when they're in closest, they'll get some of the best measurements they're looking for, but they can't do that right away. Then they'll actually pull back a bit. But anyway, that's the overall plan. So they'll be out there at the biggest distance from Psyche. They'll be 440 miles out. They'll get in as close as 47 miles. That's the plan. And this is different than the other asteroid return missions, the ones the Japanese did. Those asteroids were so small, they essentially had no gravity. The orbits that they used were really just more like they kind of hovered, and then they'd move a little bit, and then they'd hover and move a little bit more, because there just wasn't enough gravity to have much of an impact. This thing is heavy. It has gravity. It's nowhere near the weight of the moon. Way, way less than Earth, but still substantial enough to have actual orbits. Now, we were talking about the Japanese returns. We also have a sample return coming back right now, OSIRIS-REx. This thing was monitoring an asteroid called Bennu, and it's a carbonaceous rock, about a third of a mile in diameter. It was of special interest because they figured by the late 2100s there was a 1 in 2,700 chance it might hit Earth. And they thought, well, maybe it's a good idea to find out something about this. So if you're going to defend against it, at least know what you're defending against. If it's really just a loose pile of rocks, you probably do something different than if it's a really solid piece of rock. So they did a mission. It was 7 years also. This is a U.S. mission. Launched in 2016, got there in about 2018. It orbited just for a couple of years just to pick out a spot to land. Again, orbiting mean kind of hover around. You might call it a smash and grab. If you look at this picture of the spacecraft, there's this thing coming down out of it, down on the right-hand side there of the slide. They basically just pretty much jammed it down, stirred up a whole bunch of dust, and brought it back. And what they found out in doing that is this is one of those asteroids that also is called a rubble pile. It's pretty much low density, porous rocks, kind of a loose collection. But still, as a result, they managed to get lots and lots of sample. The sample return happened. It just occurred on September 24th. So left-hand side here shows you the capsule that returned in. This is landing in the Utah desert. Then they shipped it off to the Johnson Space Center for analysis. They're keeping 70% of it aside for analysis in the future, because they know that we'll get better and better instrumentation, analysis techniques, and even ideas for what to look for. And that's true, and that's a good thing that they're doing that. That's the same thing has happened with the moon rocks. They'd always put some aside, and now we've done new things that we couldn't have done in the past. Now, the spacecraft is still up there. So it's now going out to the asteroid called Apophis, which is another one that may someday come near Earth. But anyway, that's probably about 2029 they'll get out there. So this is another one of these craft where, because it uses ionic engines of one sort or another, they're pretty efficient and they can just go roaming around the universe, but they don't have time constraints. And that's why they can do that. They can take these very, very roundabout paths with gravity assist and that sort of thing that you could never do on a human mission. I guess that's pretty much it. Other space-related videos or slide presentations by me are available at the link shown here. That includes a web page and also a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of the National Space Society's North Houston chapter, and the link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.